I would like to say that I'm really very honored to speak at the conference in memory of Anatoly Moiseyevich Vershik. I was his student formally for only a year, and out of this year, 6 months I spent as an exchange student in Switzerland, so formally it was a very short interaction. I got into his orbit more or less accidentally. It was in the 90s. I was in the last year of my university studies in St. Petersburg, and I wanted to specialize in complex dynamics. But the professor with whom I was starting to work was leaving to the US, and he basically brought me to Vershik and said that, okay, maybe you could try working with Anatoly Moiseyevich. And Anatoly Moiseyevich suggested that I do my diploma work on Poisson boundaries of random walks on braid groups. At that time I knew what was a group and what was a random walk, but I had absolutely no idea that these things could be put together. It was completely mind-blowing. So as we know from Vadim's talk, Vershik thought about these things back in the 70s. This was 90s, but in my university courses I had never encountered these ideas. It was quite exotic, very interesting. And then I went on this exchange to Switzerland, and also thanks to Vershik I met people who actually were working very actively in geometric group theory. And Pierre de la Harpe in particular, who was one of Vershik's contacts and who became my doctoral advisor and now a colleague in Geneva. And so basically these 6 months that I spent working with Vershik more or less determined the rest of my career. So I'm forever grateful. And then of course for many years it was such a privilege to know Anatoly Moiseyevich and to be somehow a member at large of his seminar on representation theory and dynamical systems. And I'm happy that I was there also last December for his 90th birthday celebration that Andrei co-organized with Fyodor. And as we heard in the address by Viktor Buchstaber, who was also there, it was really such a pleasure to see Anatoly Moiseyevich at such an advanced age, but still his presence was still as magnificent as ever, and his sparkle, wonderful sparkle, was always there. So that was very, very nice to see. So today I'm going to talk about something that I hope would have interested Anatoly Moiseyevich, some limits, possible limits of graphs which are associated with dynamical systems. As Vadim mentioned in his talk, many dynamical systems allow for a symbolic interpretation. For example, if you think about an interval exchange transformation or about a polygonal billiard, then it is natural to associate a finite alphabet to it. For example, if you have a polygonal billiard, then different letters will be associated to different sides of the polygon. And then you can think about trajectories of your dynamical systems as infinite sequences in this finite alphabet. So this becomes a symbolic dynamical system, and the transformation that you that acts on this space of sequences, so for the moment it's just topological dynamical system, it is the shift. So it can be either one-sided shift or two-sided shift. And a subshift, what is a subshift? It's just a closed subset of this infinite space of sequences over a finite alphabet, which is invariant under the shift. So this is what is called a subshift or a finite alphabet, and that's the kind of dynamical systems that will interest me in this talk. Of course, if you think about the subshift, it's a set of infinite words, let's say in our alphabet A, and it's determined by the set of finite subwords that you read as part of these sequences. And also you can think about the subwords that you do not see in your subshift, and this is the set of forbidden words. And most simple, let's say, class of subshifts are subshifts of finite type, which are determined by a finite subset of forbidden words. So when you don't put any restriction, then the whole system here is called the full shift. Okay, and so as I mentioned, we can think about this as about a language, the language of words that you can read inside your sequences, infinite sequences, and the complexity function of the subshift is the growth function of this language, so the number of words of length n. So this is very basic things, of course.
Words, yeah?
Just words.
Ah, just words.
Yeah, there is no equivalence relation. Okay, so the languages that come from from subshifts, they have some nice properties. They are prolongable, so if you extend them by a letter, you're still in the language, and they are factorial, so if you take a subword, you're still in the language. So that's some natural conditions that you can put on them. And in 1980s, Rauzy, a specialist in dynamical systems working in Marseille, suggested a construction to work with such symbolic dynamical systems with the help of a family of finite graphs that you can associate with them. These graphs now are usually called by his name, Rauzy graphs. And the graphs really tell you how the trajectory of your subshift evolves. So they are constructed in the following way. The vertices of the graph, of the nth Rauzy graph, are words of length n in your language, and two words are related by connected by an edge if the end of the first word is the beginning of the second word. The end of length n-1 of the first word is the same as the beginning of the length n-1 in the second word. So you see here we have AW, W is a word of length n-1, A is a letter, and then we draw an edge labeled by B, and we become WB. So you see, if you follow the sequence of edges in this Rauzy graph, you really see how your word extends and how the trajectory of your subshift advances. Okay, so now this is a natural object, a family of finite graphs associated with a dynamical system. A general question not related to this particular sequence of graphs is the following. Suppose you have a family of finite graphs, infinite family. Is there a natural way to associate a limit to this sequence? So in one situation, there is an easy answer to that. If your graphs are rooted, if there is a specific vertex chosen in every graph, then you can, of course, look at the space of graphs with local topology. So you just look at how the balls look around your root. And if the balls look, bigger and bigger balls look the same in your sequence of finite graphs, then you say that this sequence converges. So it's just a standard local topology. So, okay, I'll go back to the previous slide later. So Itai, Benjamini, and Schramm had this nice idea how to bring this idea of local convergence to the situation when you don't have a specific choice of root in your graph. And the idea is that then you can look at your graphs as being rooted randomly. So in every finite graph, you choose your root uniformly at random. And you look at all possible routings as being uniformly distributed. And so each finite graph in your family gives rise actually to a measure, a probability measure, finitely supported measure on the space of rooted graphs with this local topology. And so in this sense, what is the Benjamini-Schramm limit of a family of finite graphs? It's not a graph, but it's the probability distribution on the space of rooted graphs. And this probability distribution is obtained as a weak limit of the measures defined by each single graph in your sequence, in your family of finite graphs. So this is called Benjamini-Schramm convergence in the space of graphs. Now, what they discovered is that these limits actually have some nice properties. So the measure that you get in the limit is what is called a unimodular measure. So very roughly you can think about it in the following way. It is a measure which is invariant under the equivalence relation, the change of the root. So it's not exactly true, but I don't want to give you the formal definition of unimodularity, but you can think about it in this way. It is, in fact, a big conjecture whether any unimodular measure on the space of rooted graphs is indeed a limit, Benjamini-Schramm limit of a family of finite graphs. So one example is that the limiting measure is actually just a delta measure on some transitive graph. So if the graph is transitive, it means that it looks the same around any vertex. So up to isomorphism of rooted graphs, it all looks the same. So just a delta measure on a transitive graph would be an example of unimodular measure on the space of rooted graphs. And if someone proves that every delta measure on a transitive graph is indeed the Benjamini-Schramm limit of a sequence of finite graphs, this would amount to proving that every a group, a finitely generated group, is sophic. So which is of course a big open question. So the question about unimodular measures in general is just a generalization of this question about sophicity. Okay, so I skipped a slide here. This is the example of Rauzy graphs associated with a full shift. So maybe you have already seen this picture. These graphs, they have a special name. They are called De Bruijn graphs because it was Nicolas de Bruijn who first introduced them, and they are often considered as finite approximations to the Bernoulli map. So they are also finite approximations, these Rauzy graphs associated with a full shift. Okay, so how I came to consider these Rauzy graphs and their limits. The story is the following. These graphs were studied, these graphs and their generalizations were studied by Deepak Dar, a well-known Indian mathematical physicist, the father of the mathematical approach to the abelian sand-pile model. And he wrote a paper which I think was seen by Vadim, as far as I remember. And the thing was the following. So they studied spectra of these graphs, computed eigenvalues, computed eigenvectors, not very rigorously. It was a physics paper in a Journal of Physics A. And in the end, there was some limiting distribution written.
This was in the context of spanning trees?
No, it was in the context of spectra of graphs. And so there was some limiting distribution written, and the last sentence of the paper was, unfortunately, there is no infinite lattice associated with this sequence of graphs. And so we have this limiting distribution, but we cannot realize it as a process on an infinite limiting lattice. And so we got interested in that, and in a joint paper with Slava Grigorchuk and Paul-Henri Lehmann, my PhD student at that time, we actually showed that the Benjamini-Schramm limit of this sequence of De Bruijn graphs is nothing else than the Cayley graph of the Lamplighter group, which already appeared in, not explained, but mentioned in Vadim's talk. So which is a very well-known object in geometric group theory, which actually was brought into the subject in the work of Vadim and Anatoly Moisevich in 1986, the seminal paper on random walks on groups. Okay, so this arose our curiosity. This is my attempt at representing this graph, the Cayley graph of the Lamplighter group with respect to a certain generating set. It is actually a horocyclic product of two regular trees. So horocyclic product means that you somehow look at your trees as being rooted at infinity by a ray, and then this defines horocycles, and you can make a product out of it. It's a standard construction. Okay, and so this is the byproduct of our work with Grigorchuk and Lehmann, is that the De Bruijn graphs provide a sophic approximation of this so-called distal leader graph, or a Cayley graph of the Lamplighter group. And so what was interesting is that this spectral distribution written in the paper of these physicists is in fact associated with the Lamplighter group. And the Lamplighter group is a very interesting example in the area of spectral theory on groups, because it is, well, I think it's not, sorry, what I'm doing, I'm also going in the wrong direction. Yeah, it's not written on my slides, but actually the Lamplighter group is the only known example of this particular Cayley graph is the only known example of a Cayley graph where the spectrum of the Laplace operator on this Cayley graph is pure point. So in all other examples where people are able to compute the spectrum of the infinite Cayley graph, it is either absolutely continuous or absolutely continuous with maybe a few delta masses added to it. And the only example of a pure point spectrum is this Lamplighter. And this result here gives an alternative way of proving that, because now you can just take this approximation by finite graphs, compute the spectra on finite graphs, which was done actually by many different groups of people, in particular by these physicists, and then go to the limit, and you just compute the limit in distribution on the infinite object, and you see that it is indeed pure point. Okay, so wait. That was my definition of Benjamini-Schramm convergence. Yes, and so Paul-Henri Lehmann, in his thesis, he studied what happens actually with the limits of subshifts of finite type more generally, and he showed that this will always be supported on a horocyclic product of trees. So there you can get not only delta measures, but also continuous measures. So there were some examples like that. And then Vadim had a student by the name of Drummond, who studied the case of subshifts of linear complexity, and showed that then the Benjamini-Schramm limit of those is always z. And in this case, if the subshift is moreover uniquely ergodic, then this Benjamini-Schramm limit, which becomes a measure on different labelings on z, so which actually becomes a shift invariant measure on the line, then this limit can be identified with the unique ergodic measure associated with the subshift. And so the question that we were interested in was, what about limits that one can associate with these Rauzy sequences of graphs of other dynamical systems, other subshifts, other than either finite type or linear complexity. So subshifts of finite type, they are always of positive entropy, so their complexity is exponential. Here we have the case of linear complexity, and of course there is a big range in between. Okay, so before telling you the result, first of all, I should say that we worked on that jointly with 3 people. Paul-Henri Lehmann, still the same person who was involved in my work with Grigorchuk on De Bruijn graphs, Sasha Skripchenko from Moscow, and Georgy Vepriv, who was one of the last students of Anatoly Moiseyevich and who is now a PhD student of mine in Geneva. And before formulating our result, I need to introduce also another component that will go in. It is the spectral convergence. So this is another way to associate a limit to a sequence of graphs. So on one hand, we have this topological probabilistic limit in terms of Benjamini-Schramm convergence. The other possibility is to look at the spectra of graphs. So to each graph, you naturally associate its adjacency matrix, and you can compute its eigenvalues with multiplicities and compute the empirical spectral measure. So this is just the averaging of eigenvalues with multiplicities. And then if your infinite graphs, if you have an infinite family of finite graphs, then you can look at the limit of these measures and try to make some sense out of it. This was done in a work by Abert, Tom, and Virag.
And the spectral density is known, yeah?
So for finite graphs, in principle, it's not known, but you can try to compute. But just whether you know it or not, you can still think about these empirical spectral measures and think about the limit. And so this is the result that you can prove that they will converge to the integral of the spectral measure on all possible infinite rooted limits integrated over the Benjamini-Schramm limit of this sequence of graphs. So this is what is written here. The empirical spectral measures on a finite family of graphs converge to the average spectral measure of the rooted limits, and the average is taken over the measure which is the Benjamini-Schramm limit. So this is in the assumption that Gn converge in the sense of Benjamini-Schramm to this random rooted graph G, a random rooted graph. So a probability measure on the space of rooted graphs, you can think about it as a random rooted graph, even though Vadim doesn't support this terminology, but still sometimes it's useful, in particular, to make sense of such statements. Okay, so we have in principle this spectral convergence, and of course I should note that in general the convergence of spectra does not at all mean that the graphs converge. So it is easy to construct examples to this effect. Okay, so that's where I remember that I did put it on the slides. This is the computation that was done for the specific case of the Brouwer graphs and of the Lamplighter group. This is the actually this pure point discrete distribution, spectral distribution on the Kähler graph of the Lamplighter, which was first computed by Grigorchuk and Zhuk. So you can also recover it by the computation of the eigenvalues on the Brouwer graphs. Okay, so this is the theorem that we proved with Lehmann, Skripchenko, and Veprev. Suppose that sigma is a subshift of sub-exponential complexity. And then the following are equivalent. As soon as the limit in the Benjamini-Schramm sense of its Rauzy graphs exists, then necessarily it should be Z. So there is nothing else that you can get as a limit for systems of sub-exponential complexity. I remind you that this was the case for subshifts of linear complexity, as was proven by Drummond. Here is a combinatorial condition on the growth function, of the complexity function, that is also equivalent to existence of the limit. So it means that this complexity function is somehow regular. So there exists a limit of its values for n plus 1 and n, and it is equal to 1. Okay, this is also equivalent to convergence in the Benjamini-Schramm sense of oriented Rauzy graphs, but this is maybe a little bit technical, so I'm not going to discuss that. And the fourth condition here is that this is also equivalent to the spectral convergence. So these Rauzy graphs will converge if and only if the empirical spectral measures converge in the sense as I described. And so there are, I would say, two interesting details, because obviously some of the implications are trivial. So two interesting points is first that the only limit that you can get is Z, and the second is that convergence of spectral measures implies convergence of graphs. Okay, so of course, we are still very interested in understanding when this similarly simple condition on the complexity function is satisfied. And some specialists in symbolic dynamics have worked on that. And so there are some sufficient conditions, mostly taken by papers, various works of Julien Cassaigne. So in particular, obviously, you know that if your complexity function behaves as a polynomial function, but also if it's not too fast. So for growth less than n to the power 4/3, for example, this also works, and this allows to already this gives us already some interesting examples of dynamical systems, for example, certain billiards and so on, which satisfy this these bounds on complexity function, and so for them the result applies. Now it's maybe a technicality that I didn't really insist on, but we can talk about these limits of Rauzy graphs in two ways. First of all, you can just think about the limit of graphs, and then the limit is a probability distribution on graphs, and we know that if it exists, it will be just concentrated on Z, so it will be just a delta measure on the line. But then if you introduce the labels, because Rauzy graphs were labeled graphs, so they were labels, letters of your finite alphabet, which were written on the edges, and then you can think about the limit in the space of labeled graphs, and then what you will get is some distribution, probability distribution, different labelings of Z in the limit. And so what we'll get will be some measures, various measures, on which are shift invariant, concentrated on Z. And so here we can compare the limits that we get with various invariant measures that can be associated with the subshift. And here we have a theorem also analog to what Drummond had proven in the case of linear complexity, that if your subshift is uniquely ergodic, and of sub-exponential complexity that satisfies the condition which guarantees that there is a limit in our sense, then the limit of labeled Rauzy graphs will exist, and it will be identified with a unique invariant ergodic measure of the subshift. So this provides you with a graphical representation of the invariant measure. So if you can think about Cayley graphs as graphical realizations of groups, right? So here is a graphical realization of the invariant measure. So in the case of unique ergodicity, unique ergodic invariant measure associated with the subshift. You realize it as a measure which is the limit of these Rauzy graphs. Okay, and so it is also interesting to understand what happens when the system is not uniquely ergodic, and it's not very easy to actually construct examples where this is concrete examples where you can compute something. So we worked with one example which appeared in a recent, relatively recent paper by Cassaigne and Caboret. They were interested in an example of a subshift, which is not uniquely ergodic, which actually means, so what they actually construct is a subshift which do not have uniform frequencies. And it turns out that in this example, fortunately for us, this condition on the complexity function was satisfied, and so our theorem applies, so we could study it in the context of our theorem. And Cassaigne and Caboret showed that the subshift provided us with two invariant ergodic measures. Okay, so we were able to compute the limits of these labeled Rauzy graphs for this example. So the limit is not unique, it depends on the subsequence of graphs that you take. And so we showed that in fact there is a continuum of subsequential limits of labeled Rauzy graphs. So each of them is a shift invariant measure to this subshift. And we were not able to find the two ergodic measures that were described by Cassani and Caboret. So in a sense, the things that come from the standard ergodic considerations and the things that we recover with this limit of graphs approach give us something different. So this is an interesting situation. We don't know, for example, whether we can construct these two invariant ergodic measures as subsequential limits of Rauzy graphs, even though, as the previous theorem shows, in the case when the measure is unique, then you just automatically recover it as a limit of graphs. But in the non-uniqueness case, we don't know how to do that, even though different subsequential limits give us other invariant measures, and here in this example, for example, we get a continuum of those. Okay, so here I think I just mentioned various classes of examples of dynamical systems where these results apply. So they have a natural coding as a symbolic dynamical systems over a finite alphabet, and there are some known estimates on the complexity functions that allow to verify that this condition on the regularity of the complexity function is satisfied, and so the theorem applies. And I think I'll stop here. Thank you.
Yes, questions, please. Talking about lamplighter group, you mean just the one-dimensional case, yes?
Yes, over Z, yes.
Yeah. Is it extendable to higher dimensions, or is it possible to relate with some kind of generalization of Rauzy graphs?
No, I think this is really so the key thing here is that the lamplighter Cayley graph is this horocyclic product of trees.
Yeah.
And as Leman showed in his PhD, for example, if you take a subshift of finite type, then the Rauzy graphs will necessarily converge to a measure which is supported on horocyclic product of trees. So that's why you recover the lamplighter group. Mm-hmm. Otherwise, yeah, it's an interesting question. Of course, Z is also trivially a horocyclic product of trees. So maybe it is actually true in general. So we know that it is true for all subshifts of sub-exponential complexity. Mm-hmm. And in the case of exponential complexity, it's true for subshifts of finite type. Now there is also exponential complexity general case. I don't know what happens there because we don't have any methods to work with that in general. Mm-hmm. But the direction in which we mostly continue this work now is the spectral computations. So the only spectral computation which is available is for this sequence of Rauzy graphs associated with the full shift, mm-hmm. the De Bruijn graphs. So the spectra of the De Bruijn graphs have been computed now, I don't know, at least by 3 different methods, by different people who were interested in them. But maybe it is possible to do that more generally for Rauzy graphs of subshift of finite type, for example, and then get, for example, in the case of Fibonacci subshift, this would give an interesting sequence which would converge to the integral of spectral measures on some infinite family of graphs. So, I mean, this may lead to some interesting phenomena, but technically it is rather complex.
Any more questions? Okay, so if not, thanks, Tanya, again. So, and